Good morning, everybody. Thanks for coming to this presentation. I'm very excited to talk about Wearable Inertial Measurement Units because actually this is my first talk about this topic. I have always talked about algorithms, machine learning, but this topic is what I really like, and I'm very excited to talk about that. Okay? As Ricardo has introduced me, I'm working in the CTPD, the Technical Research Center for Dependency Care and Autonomous Living. This is the experience of the CTPD. It's a center that belongs to UPC, and the main experience is about, as you can see, about Parkinson disease. We have had a lot of projects about monitoring patients with Parkinson disease. REMPARK, HELP, MASPARK, MOMOPA 1, SU 3, a lot of projects, so we have a lot of experience in monitoring and developing specific devices for this kind of patients. Also, we were involved in a project about fallings. It was called FATE project, in which we developed a waterproof system in order to detect fallings in real time. Then we send an alarm. Then we send also emergency calls. And now we are introducing in a new research line that is about sports. We have a very close connection with the National Institute for Physical Education of Catalonia. It's held in the Olympic part of Barcelona. And we are trying to characterize the movements of different sports in order to provide different statistics, different parameters to coaches and to physiotherapists, because they are very interested in improving the performance of basketball players, volleyball players, athletics, etc. I forgot, the CTPD created a spin-off called Sense for Care, in which now we have done a very reduced device. This is a falling sensor as well. Now we are developing the halter of Parkinson, also a reduced device for Parkinson disease patients. And well, in September or in October 2015, it's going to be launched to the market. So we are beginning a new adventure. So this is the outline of the presentation. First of all, I'm going to introduce the wearable systems. Then I'm going to explain what is inside these devices, the sensors, microcontrollers, etc. Then I will talk about the quantity of parameters, features that it has, the wearable system. And we will try to choose inertial measurement unit, depending on the application. Then after that, we will have the inertial measurement unit. I will explain the method that we are using for detecting human activity. And finally, I will explain some applications involving the project from CTPD, and at the end, the conclusions. Okay, human movement analysis has been of great interest since the 5th century before Christ. We are talking about Aristotle, Galileo, Michelangelo, Da Vinci, that they treat by means of observation, trying to model the movement, the motion of the person, making some numbers. They could model quite well some movements. As you can see, the golden number was extracted from the observation of the human body and so on. Okay, but in the 50s, 60s, there was like a boom. It was an increase in interest in the human motion, in trying to analyze the human movement. Here there is some pictures which they extract some parameters, some signals from different sensors. The first one is a stereograph vector. It's a kind of course attached to the back of the body, and it was used for to measure the linear displacement in the 3 dimensions of the space. In the other picture, you can see platform pressure. It is used nowadays also to measure the asymmetry, to analyze the gait of sports or analyze the gait of anybody. And in this picture, you can see electromyography. It consists in some electrodes attached to the skin, and it's used to measure the electrical activity of the muscles. In this picture, the last one is electrogoniometry. These are two structures with gauge that by means of its torsion and we can measure the angles of the different joints. But all these sensors are cumbersome, are invasive sometimes, they have some wire and so on. And for ambulatory monitoring, these are not very useful. This is because here we have the Wearable Inertial Measurement Unit. That this is an electronic device capable to measure, process, and store or send movement information provided by inertial sensors. Moreover, the system is sufficiently small to be portable. All of them are quite small and they are not invasive. This is the most important thing. But inside the Wearable Inertial Measurement Unit, we can find, of course, sensors. We can find accelerometers, gyroscope, etc. And then the microcontroller that gets all this inertial data, process system, and then we can find different things. For example, a storage unit to capture and to collect all the data. Some actuators, for example, buzzers to send some alarms, LEDs, or, for example, sending modules like Bluetooth, Zigbee, or GSM, GPRS modules to send SMS, calls, etc. Okay, these are the classical sensors in almost all devices. We can find an accelerometer. The accelerometer measures the acceleration in the three dimensions of the space, but in absence of movement, what we measure is the gravity, okay? The orientation against the axis of the gravity. The gyroscope, what measures is the velocity of turnings. And finally, the magnetometer, what it measures is the magnetic field. In normal conditions, what we are going to measure is the non-magnetic. I have worked some years ago with magnetometer, and it's quite annoying because I was walking through a corridor, and when I analyzed the signal, I saw that it was oscillatory, that it was showing me that I was walking, but then suddenly I had a very big noise, and then again oscillatory. This was because the sensor was measuring the structure of the building. So it's not a good idea to work with the magnetometer. Also in my lab I have a lot of noise, a lot of devices that, external agents that provides a lot of distortion to this sensor. And there are new research lines, for example, barometers that measures the atmospheric pressure. I will explain some applications later. The microphones, not to measure postural movements, but just it provides some contextualization to the postures. For example, it's not the same than being seated watching TV, or for example, being in the cinema, being in the kitchen, etc. It can provide some contextualization. And most of you wearable cameras, it's quite trending now. It's quite normal to embed cameras in wearable devices. Okay, you will say, we have smartphones, and apart of smartphones, we have a lot of applications via Android that we can download by free. A lot of applications where we can capture inertial signals, we can make some code, we can perform algorithms, etc. So you say, why using a wearable systems and if we have the smartphones? Okay, this is, I think, a nice topic of discussion, because This is my humble opinion, but we can discuss it later. For me, the smartphone has low autonomy. This means that we have to charge the smartphone every day. The sensor I have shown you before, the Angel, is a falling sensor that can last about 3 months. For me, this is autonomy, not to charge every day. And what if somebody calls you? Okay, this question is about, well, what I mean is that the smartphone is used for many things. It's used for calling, it's used to send WhatsApp, it's used to make photographs. I think this loss of time spending just the specific applications for storing, capturing inertial data, and that's all. I think that the smartphone is much more than the inertial measurement unit. Also, you know, I think it's too big. It's too big because the new tendencies shows that the mobile phones are larger and larger. So it's difficult to wear in the future. Maybe we are going to wear tablets, and it's very difficult to measure motion without being comfortable with a so big device. Also, I think that it's delicate, it's fragile. I don't know, but if you want to measure fallings, or you want to detect fallings, or you want to analyze sports like basketball, like rugby, for example, I think that you are not going to put a smartphone. In my opinion, I think that it's good for general development, for research, but it's not good for specific applications. Okay, imagine that I have sold you very well the idea that the smartphone is bad and we have to use an inertial measurement unit. Now, in this section, I'm going to talk about a lot of parameters we're going to choose, which is not the best one. We are going to discuss about different parameters, but I'm going to show you a lot of features and characteristics of the inertial measurement units. Okay. I have divided this section into 6 parts. First of all, if you see at the market, you will see like 2 groups of inertial measurement units. The first one are those ones done for data logging purposes. I mean, you put the wearable system, you get the data, and then offline you analyze the data and so on. But there are a lot another group that only provides algorithmic information. For example, the number of steps, for example, the quantity of movement performed along the day. But it's difficult to find in the market nowadays inertial measurement unit that performs both applications. Also in the market we can find, for example, from Xsense, a line that, of sensors that they are wired. I mean, they only have the inertial system, the microprocessors, and then the microprocessor sends all the information through a wire via UART, for example, to a PC. This can be cumbersome and invasive to the patient, but the truth is that these sensors are much smaller because they have less hardware. Also, we can find some sensors with Bluetooth, Zigbee, etc. to send some information. The only problem is that all this information has to be sent to a dongle, and more or less you have to be close to the dongle. So the other kind of sensors are those ones which has a storage unit, so that you can store all the data. You can go away, you can go out, and then it's not necessary to be close to a dongle. And then offline you will analyze all the data and so on. This is a new device we have developed in the CTPD. This is of course wireless. It has a GPS to capture all the coordinates, GPS coordinate. And here there is the SIM card. You see the GSM GPRS module to send SMS, some message to a server, or even making some calls. What you see here is a coil that I will explain you later how it works. I have a video. It's for inductive charge. This is for me one of the most important parts, is the where am I going to work, which is the field of applications of the wearable system. It's not the same to measure movements from the elderly applied to health, or movement for games or sports, that it involves very strong movements, and you know the elderly moves quite soft, quite smoothly, so it's not the same. I explain that because look at this graph. These are two accelerometers embedded in the same board, and I'm doing the movement that is pushing 4 times, and you can see that these accelerometers that are practically the same, they are configured differently. The first one at plus minus 2 Gs, and the second one at plus minus 16 Gs. What it happens is that when I move, I'm doing movements above 2 Gs, and when I overpass this value, I have a saturated signal. This is going to be challenging. It's going to be a very difficult thing for analyzing, because it's a this is not good, I mean. And I have to configure the sensor to 16 Gs to see all the full signal, what I have done. But you will say, okay, let's configure all the sensors to 16 Gs, this is the solution, and we finish, okay. But here is the opposite situation. What I'm doing here is to keep one wearable sensor, and what you are watching is the micro movements of my tremor. This is a zoom in, of course, but as you can see that with 2 Gs, I can see very well the signal, while with 16 Gs configuration, I have a lot of noise. This is not going to be useful for my algorithm. This happens with, because with, for example, in this accelerometer that is the same, it has 10 bits, and with 10 bits, I have to represent all the acceleration between plus 2 Gs and minus 2 Gs. And with the same 10 bits, I have to represent all the acceleration between minus 16 Gs and 16 Gs. So I have much less resolution. This is very important when you choose an inertial measurement unit, because, for example, for basketball activities, we had this problem. We searched at the market, and we didn't find any accelerometer with plus minus 16 Gs, so we did by ourselves. Okay, also the size is very important. It's, if you want to measure, for example, the movement of the fingers, you are not going to put a very big wearable system like this one. If you put the sensor in the grease the same, you have to find the comfortability for the player or for the person who is going to wear the sensor. And of course, if you wear the sensor in the chest or in the waist, the sensor can be bigger. Another important thing is the application, for example, for falling detections. One of the requirements of the project of FATE, it was that the person should wear the sensor while he or she took the shower, because a very high probability of falling there was in the, while the person was taking the shower. There is a very high probability of fall. So what we have to take into account is that the design has to be closed, has to be waterproof, and it's not easy to find this kind of sensors in the market. In the other pictures, it's a picture taken from the EPFL. This is a physiolog. He's wearing that in the wrist. It's a small sensor to measure also the acceleration, the gyroscope, and so on. But it's a very specific device, waterproof as well, to measure the movement while the swimmer is swimming in the pool. Okay, also we can find a lot of inertial measurement units which has different sensors. But this is quite trending to find 9 degrees of freedom systems, that it involves an accelerometer, gyroscope, and magnetometer in the same device. Also, we have done in our lab, I cannot see it, well, this is a dual acceleration system that, for example, for measuring smooth movements and high movements, about the problem that I was explaining before. Or, for example, one of the applications that we have done is, okay, we are going to use one accelerometer to measure the movement, and the other one to switch on the wearable device and to switch off the wearable device with a double click. I make a double click and it turns on, and when I make a double click again, it turns off. Also, we can find this board, this is very small board, where we can find a 9 degrees of freedom sensor, and also we can find a dedicated microcontroller for just to calculate the Euler angles or quaternions for navigation purposes. Also, we can find some microphones, as I have talked, and barometers. At this point, I'm going to talk about barometers. Look at this graph. You can see an accelerometer signal, a triaxial accelerometer signal, and synchronized is the barometer signal. Let me show you the levels. In this part I was walking, in this part I was going upstairs and downstairs and so on. As you can see, when I was walking, I can find an oscillatory signal, but when I'm going upstairs or downstairs, I have also an oscillatory signal, which is quite similar to walking. But the difference is that with the barometric sensor, what I find is that the signal here while I walk is quite flat. It's quite flat. But when I go upstairs or downstairs, I can see the amount of air that I have above my head. So I can distinguish quite easy if I'm going downstairs, upstairs, or walking. Also, among the barometers, we can find a lot of barometers. The signal that I have shown you before is the blue one that you can see here. These are 3 barometers that I have embedded into a wearable device. And my idea was to compare them in order to see which was the best one for human activity recognition. The first one, you can see that it's very noisy and it's only useful for detecting the different level of floors. But the second one, as you can see here, some rebounds, I will show you later. We can detect, for example, fallings. We can detect measures of less than 1 meter. The quantity of air that you have in less than 1 meter. It's amazing, well, for me. Okay, I'm going to talk about batteries. This is a very important part of wearable systems. First of all, the question of rechargeable or alkaline. The alkaline one, has more energy than the rechargeable. They are very cheap. You can find them in any supermarket. But it's suggested for very low consumption devices because at the end, they wind up in landfills. However, rechargeable batteries can be reused many times, but these ones, alkaline batteries, allows a reduced numbers of charges. This is not a good solution, and they have less voltage than the alkaline one. What about the standard AA, AAA batteries, lithium polymer batteries, and lithium-ion batteries? The first one, as I have explained before, it's not suitable for small devices because they are quite big, but due to the low voltage, usually you have to put more than one cell, so it's even bigger. The lithium polymer batteries, they are very thin and lightweight, and they also have a very good density energy, but they are more expensive. Finally, the lithium-ion batteries are the batteries which are most used. It has a high number, allows a high number of charge. It has a very high density energy, the most one. And a good feature is that it's a low self-discharge rate. It means that I can go out, I can let the device there. When I turn back, I find almost the same voltage that I had before. And the best one for manufacturers, but not for us, is that is impact by age. Somehow, after 1.5 years or 2 years, we have to change the mobile phones because the battery doesn't charge. We have many problems. The same happens with the laptops. It's fantastic for the manufacturers because somehow they force you to change the device, but it's not good for us. Also, it's a very important thing to take into account the charging method. We have developed many devices. I think that the best one, if the sensor is not waterproof, should be the standard micro USB. You know, you can use the mobile phone charger. There are many solutions, but also you can charge the battery, but you can download all the information taking advantage of the USB connection. Also, we have developed devices with a specific connection. It only allows to charge the battery, and some manufacturers somehow forces you also to buy the charger. And for example, one solution for waterproof systems is the magnetic connection. But I think that is more even better the inductive charge. In this video, you can see an example of inductive charge. I switch on the power supply. This is the charger platform. This is our device. Now I put the coil above the charger, and we can see how the current increases. It works. It's a very nice strategy for waterproof systems. Okay, and this is an example of some inertial measurement unit that we have in the market. As you can see, there are many parameters: the size, the weight, the number of sensors, the sample frequency. Sometimes it's difficult to choose one, and the main advantage of our lab is that we look at the necessity that we have, and then we can build ourselves the inertial measurement unit. Okay, once we have all the inertial data, I'm going to describe which is the method that we are using for analyzing human activity recognition. First of all, we have the sensors. We calibrate the sensors, and after that, we store all this information into a storage unit. When we have all the data via MATLAB, via the R, any software, the first that we do is to pre-process all the signal. First of all, remove all the aberrant errors due to communication errors, and then we window the signal, because it doesn't have any sense to get one sample from the y-axis, x-axis, and z-axis and analyze by itself. We have to look at the behavior of the signals in order to see what has happened. This is the windowing process. When we have one window, we extract a lot of features. We can extract maximum, minimum, deviation, standard deviation, etc. And we assign a label, for example, walking. In this window, the person has been walking, or for example, stand up, sit down, etc. With that, we build what is called the training matrix and also the evaluation matrix for develop the classifier. After that, we select the features and we normalize the feature, and this is where the input for the machine learning technique. We normally use supervector machines, but for example, in my case, I have used neural networks, tree classifiers. We can use whatever, but in our case, we use supervised machine learning. This is because we assign a label to its set of features. After we have the classifier trained by any technique of machine learning, we have to evaluate the classifier. There are many parameters to evaluate. The sensitivity and specificity are the most common, but we can use accuracy, F-score, etc. Once we have the classifier, we can build different structures of classifiers. If I only need to know if the person is walking or not, it's only necessary one classifier, and that's all. Now I'm going to talk about applications regarding the CTPD projects. In this case, I'm going to talk about Parkinson, the problematic that we have. The Parkinson disease patients goes to the doctor's office and explains the problems that they have to the doctor. Sometimes you can find a patient that can say, okay, I'm very bad, I'm almost going to die, I need a lot of medication, and then the neurologist, looking at the opinion of the caregiver and the patient and some questionnaires, provide subjective evaluation. Also, you can find the opposite situation. You can find the patient that says, no, okay, I'm regular, I can do normal life, and so on. Finally, this is a subjective evaluation. Our solution is trying to provide an objective evaluation. In the case of some symptoms, for example, freezing of gait, also we have some, there exists some tests in doctor's office, but some patients doesn't go to the doctor's office with the medication. So that the tests that are performed in the doctor's office sometimes are not reliable because, for example, in the case of freezing of gait, there are some papers that says that for cognitive issues, they don't get frozen. They don't have this kind of episodes. So the main idea is, up to now, the patients go to the doctor's office. We have a subjective evaluation. The main idea is to put one inertial system. We get the inertial data. We perform the automatic classifier, and we have an objective evaluation. Okay, this is the case of freezing of gait. Freezing of gait is a sudden inability to maintain the effective stepping movement. As you can see, the person trembles when he goes through a door, when he gets into a narrow space, he has to avoid some obstacle. Sometimes when he stands up and begins to walk, he frozen. And sometimes when he arrives to some destination. Okay. These episodes that you are seeing are not given in the doctor's office. First, because the patient is medicated, so it means that this symptom is only given when the patient is not medicated. So what we have to do is to analyze these episodes in the patient's home. How we can do that? With a wearable inertial measurement unit. Freezing of gait is detectable by means of some very famous algorithm from Moore and Backlund that what we have to do is to extract the fast Fourier transform. From that, what we are doing is to calculate the freezing index and the power index. The freezing index is calculated calculating the power of the band from 3 Hz to 8 Hz, and it's divided by the working band, that is the power of from 0.5 to 3 Hz. Then we extract the freezing index. The power index is the sum of both bands, and if both indexes goes above a trained threshold, we have a positive in freezing of gait. If not, otherwise, we have a negative. As you can see, in this signal, we have an oscillatory movement. The patient is walking, and then he sits down, so the signal is quite flat, and then when he wakes up, he has an episode of freezing of gait. So with this algorithm, we can detect quite easy the freezing of gait episode. In the basketball case, many coaches and physiotherapists wants to know the performance of a player at the beginning of the match and at the end of the match. They want to know how much they jump, how they run at the beginning and at the end, if it changes. Also, they want to know the performance in brakings, in accelerations, etc. But for doing all this, it's important to detect first the basic activity in basketball. Here are 3 simple examples. A jumping of a real basketball player. It involves 2 parts. The first one, the takeoff, the second one, the landing, and then running and walking, which is quite easy to classify because one is has more amplitude, the second one has less, and it has less frequency as well. So once we detect the basic basketball activities, we can try to measure the player performance. Then the idea is to track the player by means of complex basketball activities. But finally, what we want to know is the strategy. Strategy means how many minutes the person has been attacking, how many minutes the person has been defending. We can do that with a complex algorithm and even with cameras in order to contextualize all this activity recognition. Okay, some applications from inertial measurement units I have thought we can discuss with you later if you have more ideas and so on. What I have explained, fallings, detecting falls, epilepsy. This is one idea I have is to identify and to evaluate the number of episodes per day in order to adjust as well the medication for the patient. The apathy, which is a work of Julia now. And also for stroke, for assess the evolution of the stroke, of the rehabilitation, and in sports it has opened a very big door with a lot of ideas. I went to a meeting. I was with many coaches from different sports, and they were telling me, okay, I need to know the asymmetry of running. I need to know how much jumps the volleyball players. I need to know. There are many things, many ideas. One of them is characterized running. One of my colleagues is the teacher of a class that they are athletics and they run and so on. And one thing that they want to know is the symmetry at the beginning of the race and at the end. And also to see long, short distance performance. What I was explaining is how they run at the beginning of the race, how they run at the end, how they run, for example, in the marathon at the kilometer 10, at the kilometer 20, if the rhythm is the same, and so on. Then we can extract the same methodology for football, also for volleyball, for handball, rugby, fencing, athletics, for jumping, etc. There are many applications, many ideas to develop. So these are some conclusions. There is a wide range of applications and possibilities with inertial measurement units. Barometers and microphones are, for me, the new tendencies, are sensors that need to be work because there is not too much work done with the barometers and microphones up to now. Also, the idea of the embedded data fusion algorithms, the idea of having a microcontroller only for calculating quaternions, only for navigation, this is very interesting. We have worked with that, but we have found that it works during a short period of time. After 10-15 seconds, we are having some errors and many problems. but it's a very interesting characteristic for research. Also, the use of development boards have to choose, of course, what the methodology that we have in the CTPD is to buy development boards with different sensors, different microcontrollers, and so on. We analyze them, we work with them, and then we decide what is the best option. The sports are not exploited yet. There are some companies that begin now to put sensors to some players, but there is not too much work in research done in this field. And finally, the health applications need to be improved. The freezing of gait case, the problem that we have is that this algorithm has been trained in controlled conditions. It has not been trained in patient's home. It has not been trained with false positive protocol. And with the same case, we can extend this case to many other applications in health. There are a lot of applications and algorithms that must be improved. So there is a very wide range of applications and so on to work with these systems. Okay, and this is the end of the presentation. Thank you very much for attending. If you have any questions.